In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. For instance, consider the optimization problem: maximize f, x, y, subject to g, x, y, equals c. We need both f and g to have continuous first partial derivatives. We introduce a new variable called a Lagrange multiplier and study the Lagrange function defined by where the I term may be either added or subtracted. If f, xo, yo, is a maximum of f, x, y, for the original constrained problem, then there exists I0 such that is a stationary point for the Lagrange function. However, not all stationary points yield a solution of the original problem. Thus, the method of Lagrange multipliers yields a necessary condition for optimality in constrained problems. Sufficient conditions for a minimum or maximum also exist. Introduction. One of the most common problems in calculus is that of finding maxima or minima of a function, but it is often difficult to find a closed form for the function being extremized. Such difficulties often arise when one wishes to maximize or minimize a function subject to fixed outside conditions or constraints. The method of Lagrange multipliers is a powerful tool for solving this class of problems without the need to explicitly solve the conditions and use them to eliminate extra variables. Consider the two-dimensional problem introduced above: maximize f, x, y, subject to g, x, y, equals c. Lagrange multipliers relies on the intuition that at a maximum f, x, y, cannot be increasing in the direction of any neighboring point where g equals c. If it were, we could walk along g equals c to get higher, meaning that the starting point wasn't actually the maximum. We can visualize contours of f given by f, x, y, equals d for various values of d, and the contour of g given by g, x, y, equals c. Suppose we walk along the contour line with g equals c. We are interested in finding points where f does not change as we walk, since these points might be maxima. There are two ways this could happen. First, we could be following a contour line of f, since by definition f does not change as we walk along its contour lines. This would mean that the contour lines of f and g are parallel here. The second possibility is that we have reached a level part of f, meaning that f does not change in any direction. To check the first possibility, notice that since the gradient of a function is perpendicular to the contour lines of f and g are parallel if and only if the gradients of f and g are parallel. Thus we want points where g, x, y, equals c and, for some I, where are the respective gradients. The constant I is required because although the two gradient vectors are parallel, the magnitudes of the gradient vectors are generally not equal. This constant is called the Lagrange multiplier. Notice that this method also solves the second possibility: if f is level, then its gradient is 0, and setting I equals 0 is a solution regardless of g. To incorporate these conditions into one equation, we introduce an auxiliary function and solve. This is the method of Lagrange multipliers. Note that implies g, x, y, equals c. The constrained extrema of f are critical points of the Lagrangian I, but they are not local extrema of I. One may reformulate the Lagrangian as a Hamiltonian, in which case the solutions are local minima for the Hamiltonian. This is done in optimal control theory, in the form of Pontryagin's minimum principle. The fact that solutions of the Lagrangian are not necessarily extrema also poses difficulties for numerical optimization. This can be addressed by computing the magnitude of the gradient, as the zeros of the magnitude are necessarily local minima, as illustrated in the numerical optimization example. Handling multiple constraints. The method of Lagrange multipliers can also accommodate multiple constraints. To see how this is done, we need to re-examine the problem in a slightly different manner because the concept of a euro or equating a euro discussed above becomes rapidly unclear when we consider the types of constraints that are created when we have more than one constraint acting together. As an example, consider a paraboloid with a constraint that is a single point. the level set clearly appears to a OE cross a that point, and its gradient is clearly not parallel to the gradients of either of the two line constraints. Yet, it is obviously a maximum and a minimum because there is only one point on the paraboloid that meets the constraint. While this example seems a bit odd, it is easy to understand and is representative of the sort of a OE vector via constraint that appears quite often when we deal with multiple constraints intersecting. Thus, we take a slightly different approach below to explain and derive the Lagrange multipliers method with any number of constraints. Throughout this section, the independent variables will be denoted by x1, x2, xn, and, as a group, we will denote them as p equals. Also, the function being analyzed will be denoted by f, p, and the constraints will be represented by the equations g1, p, equals g2, p, equals gm, p, equals 0. The basic idea remains essentially the same. If we consider only the points that satisfy the constraints, then a point is a stationary point of f if and only if the constraints at that point do not allow movement in a direction where f changes value. Once we have located the stationary points, we need to do further tests to see if we have found a minimum, a maximum, or just a stationary point that is neither. We start by considering the level set of f at the set of vectors VL containing the directions in which we can move and still remain in the same level set are the directions where the value of f does not change. Thus, for every vector v in VL, the following relation must hold. Where the notation vxk above means the xk component of the vector v. The equation above can be rewritten in a more compact geometric form that helps our intuition. Is the same as writing. This makes it clear that if we are at P, then all directions from this point that do not change the value of f must be perpendicular to AF, P. Now let us consider the effect of the constraints. Each constraint limits the directions that we can move from a particular point and still satisfy the constraint. We can use the same procedure to look for the set of vectors VC containing the directions in which we can move and still satisfy the constraint. As above, for every vector v in VC, the following relation must hold. From this, we see that at point P, all directions from this point that will still satisfy this constraint must be perpendicular to AG, P. Now we are ready to refine our idea further and complete the method. A point on F is a constrained stationary point if and only if the direction that changes F violates at least one of the constraints, that is, has no component in the legal space perpendicular to AG, P. Mathematically, this means that the gradient of f at this constrained stationary point is perpendicular to the space spanned by the set of vectors Vc, which in turn is perpendicular to the gradients of the constraints G. Single constraint revisited. For a single constraint, we use the statement above to say that at stationary points the direction that changes f is in the same direction that violates the constraint. To determine if two vectors are in the same direction, we note that if two vectors start from the same point and are OE in the same direction then one vector can always or the other by changing its length and or flipping to point the opposite way along the same direction line. In this way, we can succinctly state that two vectors point in the same direction if and only if one of them can be multiplied by some real number such that they become equal to the other. So, for our purposes, we require that. If we now add another simultaneous equation to guarantee that we only perform this test when we are at a point that satisfies the constraint, we end up with two simultaneous equations that when solved, identify all constrained stationary points. Note that the above is a succinct way of writing the equations. Fully expanded, there are n+1 simultaneous equations that need to be solved for the n+1 variables which are I, and x1, x2, xn. Multiple constraints. For more than one constraint, similar reasoning applies. Each constraint function has a space of allowable directions at the space of vectors perpendicular to. The set of directions that are allowed by all constraints is thus the space of directions perpendicular to all of the constraint gradients. Denote this space of allowable moves by and denote the span of the constraint gradients by. By the discussion above, the space of vectors perpendicular to every element of If is an optimum, then any element not perpendicular to is not in allowable direction. One can show that this implies. Thus there are scalars I1, I2, Im such that. As before, we now add simultaneous equation to guarantee that we only perform this test when we are at a point that satisfies every constraint. We end up with simultaneous equations that when solved, identify all constrained stationary points. The method is complete now, but as mathematicians delight in doing, these equations can be further condensed into an even more elegant and succinct form. Lagrange must have cleverly noticed that the equations above look like partial derivatives of some larger scalar function L that takes all the x1, x2, xn and all the I1, I2, Im as inputs. Next, he might then have noticed that setting every equation equal to 0 is exactly what one would have to do to solve for the unconstrained stationary points of that larger function. Finally, he showed that a larger function L with partial derivatives that are exactly the ones we require can be constructed very simply as below. Solving the equation above for its unconstrained stationary points generates exactly the same stationary points as solving for the constrained stationary points of f under the constraints g1, g2, gm. In Lagrange unregistered trademark S honor, the function above is called a Lagrangian, the scalars I1, I2, Im are called Lagrange multipliers, and this optimization method itself is called the method of Lagrange multipliers. The method of Lagrange multipliers is generalized by the Karushia-Kiner-Tucker conditions, which can also take into account inequality constraints of the form H, X, AA permil C. Interpretation of the Lagrange multipliers. Often the Lagrange multipliers have an interpretation as some quantity of interest. For example, if the Lagrangian expression is then so, Ik is the rate of change of the quantity being optimized as a function of the constraint variable. As examples, in Lagrangian mechanics the equations of motion are derived by finding stationary points of the action, the time integral of the difference between kinetic and potential energy. Thus, the force on a particle due to a scalar potential, F equals A of V, can be interpreted as a Lagrange multiplier determining the change in action following a variation in the particle's constrained trajectory. In control theory this is formulated instead as costate equations. Moreover, by the envelope theorem the optimal value of a Lagrange multiplier has an interpretation as the marginal effect of the corresponding constraint constant upon the optimal attainable value of the original objective function. If we denote values at the optimum with an asterisk, then it can be shown that. For example, in economics the optimal profit to a player is calculated subject to a constrained space of actions, where a Lagrange multiplier is the change in the optimal value of the objective function due to the relaxation of a given constraint. In such a context I is the marginal cost of the constraint, and is referred to as the shadow price. Sufficient conditions. Sufficient conditions for a constrained local maximum or minimum can be stated in terms of a sequence of principal minors of the bordered Hessian matrix of second derivatives of the Lagrangian expression. Examples. Example 1. Suppose we wish to maximize subject to the constraint. The feasible set is the unit circle, and the level sets of F are diagonal lines, so we can see graphically that the maximum occurs at, and that the minimum occurs at. Using the method of Lagrange multipliers, we have, hence, setting the gradient yields the system of equations, where the last equation is the original constraint. The first two equations yield. Substituting into the last equation yields, so, which implies that the stationary points are and. Evaluating the objective function f at these points yields. Thus the maximum is, which is attained at, and the minimum is, which is attained at. Example 2. Suppose we want to find the maximum values of, with the condition that the x and y coordinates lie on the circle around the origin with radius h3, that is, subject to the constraint. As there is just a single constraint, we will use only one multiplier, say I. The constraint g, x, ay, minus 3 is identically 0 on the circle of radius h3. So any multiple of g, x, ay, minus 3 may be added to f, x, ay, leaving f, x, ay, unchanged in the region of interest. Let the critical values of I occur where its gradient is 0. The partial derivatives are. Equation is just the original constraint. Equation implies x equals 0 or I equals ay. In the first case, if x equals 0 then we must have by and then by I equals a0. In the second case, if I equals ay and substituting into equation we have that. Then x2 equals 2y2. Substituting into equation and solving for y gives y equals a plus or minus 1. Thus there are 6 critical points. Evaluating the objective at these points, we find that. Therefore, the objective function attains the global maximum at and the global minimum at the point is a local minimum and is a local maximum, as may be determined by consideration of the Hessian matrix of. Note that while is a critical point of I, it is not a local extremum. We have. Given any neighborhood of, we can choose a small positive and a small of either sign to get I values both greater and less than. Example 3, Entropy. Suppose we wish to find the discrete probability distribution on the points with maximal information entropy. This is the same as saying that we wish to find the least biased probability distribution on the points. In other words, we wish to maximize the Shannon entropy equation. For this to be a probability distribution, the sum of the probabilities at each point must equal 1, so our constraint is. We use Lagrange multipliers to find the point of maximum entropy, across all discrete probability distributions on. We require that. Which gives a system of n equations, such that. Carrying out the differentiation of these n equations, we get. This shows that all are equal. By using the constraint. We find. Hence, the uniform distribution is the distribution with the greatest entropy, among distributions on n points. Example 4, Numerical optimization. The critical points of Lagrangians occur at saddle points, rather than at local maxima. Unfortunately, many numerical optimization techniques, such as hill climbing, gradient descent, some of the quasi-Newton methods, among others, are designed to find local maxima and not saddle points. For this reason, one must either modify the formulation to ensure that it's a minimization problem, or else use an optimization technique that finds stationary points and not necessarily extrema. As a simple example, consider the problem of finding the value of x that minimizes, constrained such that. Using Lagrange multipliers, this problem can be converted into an unconstrained optimization problem. The two critical points occur at saddle points where x equals 1 and x equals a 1. In order to solve this problem with a numerical optimization technique, we must first transform this problem such that the critical points occur at local minima. This is done by computing the magnitude of the gradient of the unconstrained optimization problem. First, we compute the partial derivative of the unconstrained problem with respect to each variable. If the target function is not easily differentiable, the differential with respect to each variable can be approximated as, where is a small value. Next, we compute the magnitude of the gradient, which is the square root of the sum of the squares of the partial derivatives. Since magnitude is always non-negative, optimizing over the squared magnitude is equivalent to optimizing over the magnitude. Thus, the square root may be omitted from these equations with no expected difference in the results of optimization. The critical points of H occur at x equals 1 and x equals a 1, just as in I. Unlike the critical points in I, however, the critical points in H occur at local minima, so numerical optimization techniques can be used to find them. Applications: Economics. Constrained optimization plays a central role in economics. For example, the choice problem for a consumer is represented as one of maximizing a utility function subject to a budget constraint. The Lagrange multiplier has an economic interpretation as the shadow price associated with the constraint, in this example the marginal utility of income. Other examples include profit maximization for a firm, along with various macroeconomic applications. Control theory. In optimal control theory, the Lagrange multipliers are interpreted as costate variables, and Lagrange multipliers are reformulated as the minimization of the Hamiltonian, in Pontryagin's minimum principle. See also, duality, Karushia-Kiner-Tucker conditions, generalization of the method of Lagrange multipliers. Lagrange multipliers on Banach spaces, another generalization of the method of Lagrange multipliers. Lagrangian relaxation, references. External links, exposition, conceptual introduction, Lagrange multipliers for quadratic forms with linear constraints by Kenneth H. Carpenter. For additional text and interactive applets, simple explanation with an example of governments using taxes as Lagrange multipliers, Lagrange multipliers without permanent scarring explanation with focus on the intuition by Dan Klein, applet, video lecture of Lagrange multipliers, MIT OpenCourseware video lecture on Lagrange multipliers from multivariable calculus course, slides accompanying Bertzkas's nonlinear optimization text, with details on Lagrange multipliers, Kipid's blog, Optimization with Constraints, Method of Lagrange multipliers, general explanation about the method of Lagrange multipliers. Additionally, method of Lagrange multipliers with complex variables, and approaching method to minimum-maximum from initial guess are explained. Geometric idea behind Lagrange multipliers.